Hi everyone. Today we will discuss about theory of specific heat. So we say that the lattice vibration is an important one to say the or to predict the thermal properties of a solid. So if thermal properties like specific heat, these are depends upon the vibration of lattices in normal modes. Okay. Okay. So here we'll first of all address what is specific heat means. So as you all know, it is the amount of energy required to rise the temperature of a 1 mole gas by 1 degree Celsius, which is called specific heat. If you want to increase the if it is amount of energy required to rise the temperature of 1 kilogram of gas, you can just simply say that is heat capacity. So since it's 1 mole of a gas by 1 degree Celsius, so we can say that there is specific heat capacity or specific heat. Okay, and specific as we can know that this can actually represent as dq by dt, where c is actually the specific heat, where q is the dq is the amount of energy for a particular time interval. Okay, so you can see there are two type of specific heat case. One is cv, another one which is cp. So cv means it is actually specific heat at constant volume. Okay, specific heat at constant volume, as you can see, and this is actually specific heat at a constant pressure. So there are two type of specific heat. One is specific heat at constant volume, another one is specific heat at constant pressure. And you can see there is a relation that is for an ideal gas. If you say, so we have an ideal gas situation. In that case, we have an equation that is Cp minus Cv is equal to R. This relation also called as Mayer's relation. Cp minus Cv is equal to R, where we know that the Cv, the specific heat means at constant volume means you are actually supplying a heat Q outside from the object, and you are actually increasing the internal energy of that gas molecule. Whereas in the specific heat capacity at constant pressure means you are actually introducing a heat which used to increase the internal energy. Also, it will also work done against the external pressure as well. So as you can see from this expression, the specific heat capacity at constant pressure is more than CEV, as you can see from this expression as well. So that is comparably high because it is used to increase the internal energy, and there will be also work done against external pressure also there in the case of specific heat capacity at constant pressure means. Now we were interested to discuss the specific heat of a solid. Okay, so we'll are more interested in the case of how the specific heat of capacity of a solid depends on what are the different parameter which mainly determine the specific heat of a solid. Okay, so what is the difference in solid? So what is the difference in solid compared to liquid and gas? So when you say about thermal expansion, so the thermal expansion is gas for gas is greater than liquid, and it is greater than solid. So this is a case of thermal expansion for gas, liquid, and solid, and you can see that solid do not expand much. So we do not expand much on heating. So if you do some give it some an amount of energy, or if you are heating a solid, you can't see there'll be a much expansion, means thermal expansion you cannot see in a solid case. So in that case you can actually say that the Cp is approximately equal to Cv, and that is equal to C. So that is Cp is equal to Cv in the case of a solid. So that means the solid do not expand on heating, so C will be, you can simply take it as Cv. So in most of the case, specific heat of solid we represent in terms of CV. Okay, in terms of CV. And now in solid cases, when you consider a solid, there are two main ingredient you can see. One is a positive ion core. So in a solid, if you consider, so there are two cases you can see. A solid is made up of a positive ion core and a free electrons are there. Okay, for example, in the case of Na plus and Cl minus, where Na plus is the positive ion core and Cl minus is actually the free electron, or which has a negative ions, right? So if you simply just take Na plus, we'll have a positive ion core and there will be a free electron as well. Okay, in the case of a sodium. Okay, so that means you can expect through two components there. One is a positive ion core and another one we have a free electron in that case. Okay, so significantly if we take the case of sodium. Okay, so if Na is ionized, in that case it will be a positive ion core and we have a free electrons also available in that case. So when you say the specific heat of a solid which has a two physical mechanism one can expect there. So one is due to this positive ion core. So if I say the specific uh, heat of a solid, so it depends on two parameter basically. Okay, so first parameter which is which I mentioned, the positive ion core. Okay, positive ion core, and we are also having a free electrons. Okay, so when you consider a crystal or a solid which has a positive ion core and a free electrons, so you can see that this positive ion core will execute a motion. Okay, so we'll have a motion of positive ion core in the case of a case. uh, in this scenario you basically see that this positive ion core is responsible for lattice vibration. Okay, so the dominant contribution is from positive ion core for lattice vibration. And you can see that in free electron case, still there you can also see that motion will be there, but it generally execute a thermal motion compared to here. Okay, it generally execute a thermal motion rather than a lattice vibration case. So you can also see that if it is a lattice vibration is there, and lattice vibration is the dominant contribution towards the specific heat case, so and then you can this specific heat you can also call out phonon specific heat. So your phonon specific heat, and there will be also have a electron specific heat, free electron or electron specific heat. So you can see that in solid case there will be two contribution. One will be from the free electron side and another from phonons or the lattice vibration, which the lattice vibration is originating from the movement of positive ion core. Okay, hope it is clear. Now we will be addressing the different theory due to specific heat. Okay, so there you can see uh, we say that there will be two contribution. So firstly we'll be addressing the contribution from the lattice. So we have a couple of theory. Okay, theory of lattice specific heat or phonon specific heat. Okay, so we have a theory of lattice specific heat. So in this case we have two kind of theories you can see. One is called classical theory. Okay, which is called classical theory, and which is also names as Dulong-Petit's law. Dulong's Petit law. And we, since we have a classical theory, definitely we should have a quantum theory as well. Okay, so we have a quantum theory as well, so which is also called as, in quantum theory we'll have two representation again. There will be two classification you can see. One is called Einstein's theory, another one which is called Debye theory. Okay, Einstein theory and Debye theory. Okay, so we'll address these each one in detail. So first of all we'll take classical theory. classical theory, which is called Dulong Petit law. So in Dulong Petit law, so it is assumed that since it's a theory, right? So it's assumed that the atoms in a particular crystal or a solid, okay, which vibrate like a which is actually vibrate like a simple harmonic motion, okay, or simple harmonic oscillator. So rather that will be better, simple harmonic oscillator, okay. So SHO means simple harmonic oscillator, and this simple harmonic oscillator is having three modes of vibration as well, okay. If it is a three-dimensional one, there will be three modes of vibration. And we say that classically when you consider we consider that these atoms are actually identical. So we say that these atoms are identical, and which is actually act as a classical harmonic oscillator, okay. So we consider as a classical harmonic oscillator which is execute a simple harmonic motion, okay, oscillator, okay. So we say that this classical or harmonic oscillator which is vibrating with the same frequency as well, okay. The frequency of each harmonic oscillator or each atom is actually same fundamental frequency, okay, which is independent of the each other, okay. And now we say that we have a single atom, okay. So each atom will be having three dimension, so there will be three modes of vibration also, okay. And now we say that if there are n atoms, okay, so if I have n atoms, so definitely this will be having a 3n modes of vibration that we already discussed. So when you say the energy of an harmonic oscillator, so the energy of the harmonic oscillator, energy of this harmonic oscillator, you can say that that is equivalent to 3 kBt, where kb is a Boltzmann constant, okay. So it's Boltzmann constant. So Boltzmann constant means 1.38 in 1 raised to minus 23. So that is a Boltzmann constant case. And now we can say that we consider, okay, so we consider for a harmonic oscillator, for a classical harmonic oscillator. So we can say that which we take it as one dimensional, one day, okay. So the total energy is equal to, which we can say that that is equal to E is equal to 1 by 2 mx dot square plus mx dot square plus 1 by 2 kx square, while 1 by 2 mx dot square means it is representing the kinetic energy, and the second part is actually the potential energy. So that is the total energy of a classical harmonic oscillator in one dimension. And now if you consider this in 3D, so if you consider in 3D, so here the energy will be having six terms, because we have 2 will be due to x and 2 due to will be y, and if you consider x y z direction, so we'll be having three kinetic energy terms, and we'll have three potential energy terms in three different directions. So okay, so each energy will be contributing in a half kBt. So each energy will be contributing in a half kBt. So you can see that if you have a three-dimensional case, this total energy, you would have studied the equipartition theorem in the case of statistical mechanics. So they will be consider that each energy, this is equivalent to a half kBt, okay. This is equivalent to half kBt, this is also equivalent to half kBt. And similarly you can see that in three-dimensional, you can see that there will be half kBt is a single particle energy, so that is into 6 will be there, because 6 dimension if you consider, okay. Okay, so that this will be equal to the, this will be, you'll be getting as 3 kBt as the three dimension, the total energy in the case of a three-dimensional case. So if in one dimensional, you will be having half kBt. In three dimensional, you will be having 3 kBt as a total energy. Okay. Now, if I say the internal energy, so this is actually the internal energy of a particle. This half kBt, 3 kBt means it is the internal energy of a classical harmonic oscillator in 3 dimension. Okay. Now, we say that internal energy of a classical harmonic oscillator. Okay. Uh, Let me just put that n classical harmonic oscillator. So let me have n atoms. N atoms of the total energy will be 3n kBt will be there. 3n kBt. 3n kBt. And this you can actually represent as E is equal to 3RT, and then where R is actually nkb. This expression is actually R. So this is an equation that you want to see. So this is actually the internal energy of a classical harmonic oscillator in three dimension for n particle, for n particle. So you can see that the energy is actually proportional to what? Temperature. So energy is proportional to temperature. Now we know, so if we consider this total energy as internal energy U, okay, so we can also consider the specific heat will be, the specific heat will be dE by dt. So the specific heat will be at constant volume will be equal to dou E by dou T or dE by dou T. So when you differentiate this one, you can get that will be 3R. So you can see that according to classical theory, so according to classical theory, you can see the specific heat, the specific heat is constant at all temperature, at all temperature. So that's what this equation is all about saying. So you can see that Cv will be a constant value. So when you picturize it in a graphical format, so you can see that we have a Cv on the y-axis, we'll have a temperature. So it says that the Cv will be having a constant value throughout the temperature. So that's what this expression is all about saying. Okay, but there's a point we need to say, but we have an experiment. So we already have a quantum theory, right? Why we need a quantum theory? So we'll discuss that. So but experimentally, if one could see that, experiment shows that this quantity, the Cv is constant at all the temperature, that assumption is wrong, or that finding is wrong, because when you do experiment, you can see that at low temperature, you can see that the Cv is actually proportional to T cube. Okay, but according to classical theory, it says that at all temperature specific heat is constant, but experimentally one can find that the specific heat capacity is proportional to T cube at low temperature. So that experimental evidence, okay, is failed to explain by this particular classical theory. So classical theory cannot explain why there is a T cube dependence on a specific heat at low temperature. So at that scenario, there is another theory come into picture, that is called quantum theory of lattice specific heat. So which is also called, there will be two type. One is Einstein's theory. Okay. So we'll see the next quantum theory cases. Quantum theory here. In that, firstly, we will be addressing Einstein's theory. So in Einstein theory, what is trying to explain is that, or what is assuming is that, he's saying that in classical theory we consider all the atoms is vibrating in a vibrating as a simple harmonic oscillator, that too a classical harmonic oscillator. But here, what we do is that we say that in Einstein's theory, he considered this atom is actually vibrating in a simple harmonic motion, and that atom is considered as a harmonic oscillator, quantum harmonic oscillators. Okay, and you can see that this is actually vibrating at a condensed frequency. These atoms are vibrating at the condensed frequency. So, which says that all the atoms are in being same frequency. So he's considering that all the atoms will be having the same frequency. That was his assumption, is that that means all the atoms which is vibrating at a particular energy will be having the same energy. So that's that it means. So you can see that the frequency is condensed in terms of quantum number, that's n is equal to 0 1 2 3, that is the expression. And you can see that the energy of a one dimensional quantum harmonic oscillator, it is condensed. So that is En is equal to n plus half h cross omega. En is equal to h cross omega, where n can take the value 1 2 3 etc. Okay, so these are the value where n is actually the quantum number. Okay, okay, so you can see that. So when you consider at a particular temperature T, so the average energy, if we consider the average energy of harmonic oscillator, will be E bar, that is average energy. So that is half H cross omega. Half, so this will be the expression for that. Okay. This part of the discussion, this theory of specific heat discussion, maybe you have extensively studied in your statistical mechanics case as well. Okay, so I am not going very detailed into that. Okay, so you can see that this half h cross omega is actually not thermal uh, energy, which represents the condensed energy of a harmonic oscillator. And you can see that for a one dimensional harmonic oscillator, so this is can be the case if there are n atoms. Okay, we have n atoms which is vibrating like a quantum harmonic oscillator, and which is actually in three dimension. If we consider, okay, we have an atom which will have a three dimension. So you can see that the total number of modes will be what, it will be 3 n modes you can expect. Okay, so you can also consider that, which is equivalent to considering this representation E bar is equal to 3 n h cross omega by 2 will come, plus 3n h cross omega by e raised to h cross omega by kbt minus 1 will be coming into the picture. Okay, now what I supposed to, sorry, this is average energy, not so vector quantity. Okay, so it's average energy. So you can see that this is the internal energy of a quantum harmonic oscillator, which is in three dimension for an atom's case. So now our goal is to find the specific heat capacity dependence on temperature. How the specific capacity is depends on the temperature. Whether it is validating the evidence of experimental evidence, that is CV is proportional to D cube. Okay. So here you can see that we are actually taking dou E bar by dou T. Okay, dou E bar by dou T. So that is CV. When you take this equation, this is the E bar. So when you take the dou by dou T, you will be having 3 n h cross omega. Uh, e raised to h cross omega by kbt will come into picture, minus 1 into raised to minus 2 will come here. Okay, and e raised to h cross omega by kbt into h cross omega by kb, okay, minus 1 by t square. This is how the expression when you differentiate this with respect to dot t. because the first term is goes 0 because there is no dependence on time, sorry, temperature. And the second term you can see a dependence on temperature because it's e raised to h cross omega by kBt. So when you do the differentiation of this one, you can see that that is minus 3 n h cross omega e raised to h cross omega by kBt minus 1 raised to minus 2 e raised to h cross omega by kBt into h cross omega by kb, and you will be have 1 by t here, you will be having a minus 1 by t square representation. And now if you make this equation like this, 3n h cross omega whole square divided by kb, 1 by t square will come, 1 by t square e raised to h cross omega by e raised to h cross omega by kbt divided by e raised to h cross omega by kbt minus 1 raised to square. So if you rearrange these atoms in this fashion, you can actually write Cv is actually 3 n h cross omega square by kb 1 by t square e raised to h cross omega by kbt by e raised to h cross omega by kbt minus 1 square. Now here actually you can put theta e is equal to h cross omega by kbt, sorry, kb. Okay, so what it means is that which is called as Einstein's temperature. Einstein temperature. Okay, Einstein's temperature. Okay, so here if you put this value Einstein's temperature in the representation, this Cv will be transforming into, you can see that Cv is equal to 3R. Okay, so it will be 3R theta E by T square e raised to theta e by t divided by e raised to theta e by t. This e is actually subscript, you have to see that, minus 1 square will come. So this is how the expression for theta is the Einstein temperature. So this is the expression for specific heat capacity in Einstein's theory. Okay, so you can see that this Einstein temperature is actually a reference temperature. So with that temperature you can actually compare the value of your applied temperature. So this you can this will be the representation. Cv is equal to 3r theta e by t square e raised to theta e by t e raised to theta e by t minus 1 square. Now in this case we'll address two particular cases. We have a case at high temperature. Okay, so we'll consider this equation at two different temperature case. So at high temperature means you are actually consider that h cross omega will be very less than kBt. Okay, and theta in that case it will be a comparably low temperature where T is applied temperature and theta is the Einstein temperature. So you can say that in that case theta e raised to theta e by t will be a very small value. It will be a very small value or very small value, you can say that. And in that case this expression you can actually modify the Cv expression. You can actually simply write as 3r theta e by theta e by sorry theta e by t square e raised to theta e by t divided by, we'll have an expression, right? So what we do here is that e raised to theta e by t minus 1 square is there, no? So we can actually binomially expand this equation here. So we'll have 1 plus e raised to theta e by t minus 1 will come. Okay, so e raised to theta e by t minus 1, you can actually this or rather e raised to theta e by t you can actually binomially expand. So this how the expression will be. Okay, if you expand this term e raised to theta by t minus 1. So what it means is that you can actually cancel out e raised to theta by t from this expression. 1 plus 1 minus is here, so 1 and 1 get cancelled. E raised to theta e by t by e raised to theta by t. So you can actually cancel out what, you can actually cancel out the term and you will be getting okay, sorry, 1 second. Okay, so okay, there is an expression you have to make it. Okay, so this becomes actually theta e by t, because e raised to theta e by t is a very small quantity. So this will be theta e by t here. And you can say that e raised to theta e by t is a very small value. So we can actually neglect this. So what is the in numerator term? The terms in the numerator you can actually neglect. So you'll be having a representation Cv is equal to 3r into theta e by t square divided by theta e by t left. So you can cancel out this theta e by t each other, and you can get the term Cv will be equal to, okay, there's a square over here, sorry. Okay, so you'll be getting us 3r. Okay, so 3r. So what it means is that you can see that here also at high temperature, which is matching with the classical theory. So classical theory say that Cv is a constant at all temperature, but in Einstein case you can see that at high temperature Cv is actually constant. So when you say that at high temperature Cv is constant at a high temperature, okay, Cv is constant at a high temperature. Cv is constant at high temperature. Okay, and now we see the another case, that is case 2. So that is we'll be considering at a low temperature. So at low temperature means you can say that H cross omega is actually greater than KT. KT is at applied temperature, and you can see that in that case the Einstein temperature will be greater than the applied temperature. Okay, so your Cv becomes in that case theta r, theta e by t whole square, e raised to theta e by t, and then in denominator you can say that this equation becomes what, uh, one, you have a term e raised to theta e by t minus 1. So we say that this quantity will be much higher than 1 e raised to theta e by t. So in that case this you can actually neglect 1. Okay, so we'll have e raised to 2 theta e by t. Okay. Sorry. And the Cv will be in that case it is 3r theta e by t square. Okay, and this becomes e raised to minus theta e by t, this equation. Okay, so this is how this equation will look like at low temperature. So you can say that there is an exponential term is actually there in the specific heat capacity. So that means at low temperature, okay, at low temperature the specific heat is actually decreasing exponentially with the decreasing temperature. Okay, so you can see that there is a dependence on specific heat capacity on exponential term. So at low temperature the Cv is decreasing exponentially, like e raised to theta e by t. Okay, with respect to decreasing temperature. As the temperature goes down, the Cv also goes down in a case of specific heat capacity at low temperature. So when you see, when you graphically represent that, you can see that this graph will be like this. We have Cv here, we have temperature here. So this is actually exponentially on a decreasing fraction on the, you know, in this route, and it will achieve a constant value. And this is the point where called high temperature region. Okay, so it constant at high temperature, so at high temperature it has a value 3r. Okay, so you can see that again here in Einstein theory also what we can observe is that uh, at low temperature the specific heat capacity depends on e raised to minus theta by t. It is actually exponentially decreasing with respect to temperature. So again we say that, but experimentally what we observe, experimentally we say that the specific heat capacity is actually proportional to T cube. Okay, so this Einstein theory also failed to explain that. Einstein theory also could not explain why there is a specific heat capacity is proportional to T cube. Also it cannot find the dependence on, also it cannot find the dependence on specific capacity on T cube. So what we expect is that, our expectation is that at our expectation at low temperature, our experimental finding says that Cv is proportional to Tq, but Einstein theory is also failed to explain that or prove that dependence at a low temperature. So we'll see another theory that is we already mentioned about earlier, that is called Debye theory. Okay, so we'll introduce Debye theory at this point. So what Debye theory is, this says that it's again a quantum harmonic theory. So it's again a quantum harmonic theory. Okay, so it's a quantum theory. So we know that in Einstein theory we consider that we have a n harmonic oscillator. So this n harmonical oscillator will be vibrating with the same natural frequency. I have mentioned that. Okay, that means the frequency is actually independent on the each atom. So in each atom it having the same frequency. So it is treat the total energy as the average energy of this collection of all the particles vibration. And but in Debye theory, what he is assuming is that, he is assuming that it is again a quantum harmonic oscillator. So we have a quantum harmonic oscillator again. Okay, with a different frequency. Each atom will be having different frequency here. Okay, so we have a collection of frequency, so we have a collection of energy, so different energy, different frequency there. So we know that if we have a different frequency, we have a different energy. E is equal to h nu. Okay, so that is the case. So we have a collection of energy, so we have a collection of frequency in this case. So in that case, we consider that we have a collection of frequency, means we take a considering the density of state. So density of state is actually proportional to nu square. What is density of state means? Density of state means it's actually the number of uh, particles at the same energy level, okay, or a particular frequency level. So it is called density of state. So you can see that the density of state of a density of state of an electromagnetic radiation, it is actually, you can see that d of E is actually proportional to E square, where E is a energy. So it is an energy representation, you can see here. So in density of state, we normally consider the number of energy state available per a unit energy cases. Okay, so if you want to know what is exactly density of state, you can have this term. So we have a number of energy. Okay, we have a number of energy states available per unit energy interval. Okay, so we know that as the frequency, the nu means the frequency, if it is increased, d of nu also will increase, depends upon that. So we can see that we considered already the case of uh, crystal, where two type of wave can propagate in a solid. One is called longitudinal wave. Okay, so in we already discussed that for a longitudinal wave we'll have only one mode of vibration per harmonic oscillator. Okay, that means the propagation of wave will be along the direction of wave. And there's another type of wave which is called transverse wave. A transverse wave will be having two modes of vibration. One will be perpendicular, and the vibration will be perpendicular to the direction of propagation. And the specific heat we are going to represent here which is comes to be like this. We'll see that expression here. Okay, here the CV is going to be, will have the value 3r theta d divided by t raised to, so no value for, it will be theta d by t into fd, whereas fd means it's actually called Debye function. Okay, it is Debye function. So you can actually say that CV is actually, when you expand that, it is CV, sorry, 3r into theta d by t into 3 into t by theta d raised to 4 integral 0 to theta d by t. Okay, e raised to x by x raised to 4 divided by e raised to x minus 1 square. Okay, dx. So this is the main expression of specific heat capacity at, in the case of Debye. So the difference is that Debye consider each atom having different frequency compared to the other one. So we'll have a collection of frequency and we'll have a collection of energy in that case. So here you can see an expression of theta d. So theta d means it's actually Debye temperature. Okay, so Debye temperature means it is actually h cross omega d by kb. Okay, so where omega d is actually Debye frequency. Okay, you can say that this is Debye angular frequency. And this expression you can also write like this, h nu d by kb. Okay, you can remove that h cut there, h nu d by kb. So that is the Debye temperature expression, theta d. Okay, and here you can see that again this theta d we consider as a reference temperature, like an Einstein temperature case. So here we'll consider uh, like the earlier case, we case 1, case 1 at high temperature. Okay, at high temperature, at high temperature you can see that h cross omega d, or rather h nu d. Okay, h nu d, this is actually h not b, you should not confuse that. Okay, h nu d, it's very greater than kbt. Okay, and that is theta d is actually very greater than the applied temperature t. So if, when you see this expression theta d by t, in that case you can see that e raised to x, x raised to 4 divided by e raised to x minus 1 square, and this expression will take the value pi raised to 4. Okay, pi raised to 4 divided by 15. So this function, this is actually a function. So when you evaluate this function, you'll be getting the value as pi raised to 4. Okay, so that your CV will be, you can write it as 12r. Okay, 12r t by theta d cube. Sorry, I am mistaken. So that was an expression for low temperature. Okay, so here is theta d is actually very greater than so so again there will be correction here. Okay, sorry. So here you can see that h cross omega d is equal to h nu d, which is very greater than less than kbt. Okay, so that is this theta d is much less than the applied temperature. Okay, for this region we can say that 0 to theta d by t, theta d by t, e raised to x, x raised to 4 divided by e raised to x minus 1 square. Okay, dx, which will be having the value 1 by 3 theta d by t square cube will come. Okay, so that means if you put this expression into your CV, you can see that CV will be getting us again 3R. Okay, so this expression 1 by 3 theta d by cube. So you can see this CV. So if you substitute that here, if you substitute here, you can get that expression theta d by t cube will be getting cancelled. Okay, it will be getting us 1 by 3 CV will be there. So what it means is that at high temperature, at high temperature, debate theory will match with what? Match with the classical theory and Einstein theory. Okay, theory and Einstein theory. Okay, so that is CV is constant. At high temperature, the specific heat capacity will be constant. So debate also satisfying that, and you can consider the case 2 here. So it is at a low temperature. So that is an important case here because we are interested in this particular case. So h nu d will be very greater than kBt here. So that is theta d is actually very greater than the temperature. So here in this expression theta d by e raised to x raised to 4, okay, divided by e raised to x minus 1 square, and that term will be equal to, you can say that is pi raised to 15 will be the value of that expression. Okay, so if you substitute that into the CV, you can get the CV will be equal to 12R T by theta D cube, okay, pi raised to 4 by 15. So this is how the expression will be there. Okay, and that means you can see that there is a relation. Specific heat capacity is actually the CV is proportional to what? It is T by theta D, T by theta D cube. Okay, that implies CV is proportional to what? T cube applied temperature. So we can say that at low temperature, at a low temperature, we can see this expression for according to debate theory. So we are able to satisfy. So this is actually this result. So this result matches with the experimental evidence. Okay, experimental result. Okay, so that we can say that debate theory is the best theory compared to the other one to explain. So which explain the specific heat capacity on the temperature dependence. Okay, so which is properly explains how the temperature will be depends upon the temperature, sorry, specific heat capacity, how it depends on the temperature at low temperature and at a high temperature. Okay, so that is a main concept here. So you can see when you consider the internal energy. So okay, let me just okay. So we can see that the internal energy of lattice vibration. Okay, so which is also we can call as the phonon energy. Okay, so at a high temperature, this internal energy either you can take it as E or you can take it as U. Okay, so that is proportional to T. At a low temperature, you can see that E is actually proportional to what? It will be T raised to 4. So that's why you are getting CV is equal to T cube. Okay, and when you examine this debate temperature in much more detailed way, okay, so you can see that this debate temperature expression, this theta d, you can actually write as h nu by kb, okay, 6 pi square n by v raised to 1 by 3. So that is a much more detailed way of expressing that debate temperature. So where you can say that this is actually not new. Okay, this is v. Okay, so where v is actually velocity of sound, and this is a capital V you can see here. So that is a volume, and where you can see that n is the number of atoms present in the solid. Okay, and if you represent n by v, that is means the atomic density or the number density. Okay, so the theta d, the debate temperature will be different for different solid. Okay, theta d is different for each solid that you want to see, because the number density of each solid will be different. Okay, because particularly if you take the consideration of a BCC lattice, if you consider, so this lattice have a lattice parameter, let me say that that is a 2 angstrom, and the velocity of sound is supposed to be 1000 meter per second. Okay, and in that case if you calculate the theta d, it will be different. So you can use this particular equation to find the debate temperature for different velocity. So here v is actually velocity, not the frequency that you want to specify, and the capital V here, which is called the volume. Okay, so this representation you can see here. And finally, to end up this session, let me have one more point to add. So you have, when you consider the specific heat, total specific heat will have two contribution. One is from the lattice, the other one is from the electron or the free electrons. Okay, so we say that at lattice cases, we see that at high temperature, we say that C is proportional to what? It is T raised to 0 or it is constant. T raised to 0 means it's 1. So C is proportional to TQ at a low temperature. So you can say that the Debye able to successfully explain the dependence of specific heat capacity of lattice vibration on temperature at high temperature and low temperature. Okay, but Debye could not explain the specific heat capacity due to electron. Okay, so Debye only could explain the specific heat capacity due to lattice vibration, that we already have seen that here also, but there is again a contribution of electrons as well for a specific heat capacity. So that we will be discussing in the next module, where we will be discussing about free electrons, because in free electron case we have a situation that we have the potential energy will be zero for a free electron. The free electron only have a kinetic energy. Okay, so the energy will be 3 by 2 kBt for a case of a free electron. Okay, so it does not have a 3 kBt. So when you consider the electron case, the internal energy of a free electron, so you'll have, if you consider the potential energy will be 0. Okay, plus we'll have a kinetic energy. Okay, this potential energy will be 0 for a free electron. For a free electron, this will be 0. Okay, so that is for a free electron will only have kinetic energy. That means, if you consider a three-dimensional particle, that will be 3 by 2 kBt. So this is the expression of energy. Okay, so we'll see what is the lattice specific heat. Sorry, what is the electronic specific heat. So we just discussed only case of the theory of specific heat due to lattice vibration. There is one more aspect we need to discuss, that is the theory of specific heat due to electron or electronic specific heat. So that part we will be discussing in the next module, where we will be discussing about free electron theory. Okay, so I think at this point we can end this session. So we've just discussed about theory of specific heat, where we have seen there will be two contribution will be there for specific heat, one from positive ion core, another from free electron. So we only discussed on the contribution from lattice vibration. So in order to explain the theory of specific heat due to lattice vibration, there are three theories. One is classical theory, which is called Dulong-Petit law, and the next one, which is called quantum theory. In quantum theory, we have two theory, which is called Einstein theory and Debye theory. And comparing the all the three theories, where Debye could successfully explain the lattice specific heat at a low temperature and high temperature, where at high temperature the specific heat capacity at constant volume is constant. At low temperature, specific heat capacity is proportional to T cube, the applied temperature. So that was the main inference. When in classical case, we are considered as a classical harmonic oscillator. In quantum case, in Einstein theory, we consider as a quantum harmonic oscillator with the same energy, same frequency for all atoms. But in Debye, what he has changed is that he considers that we have a n quantum harmonic oscillator. Each one have different frequency and correspondingly different energy, so that we will be considering the density of state, density of energy. Okay, so that's what we have discussed today. And we have one more contribution also towards total specific heat, that is electronic specific heat. So that we'll discuss in the coming modules. Okay, thank you.